number, and usually it's very, very strong. So you can see, as in this example here, it's 1718, so around 1710, and it's a very narrow and very sharp, very strong peak. So usually it's the strongest peak in the IR spectrum. So if you see a very narrow and large peak, I would not say large, but strong peak around 1710, it's very likely that it's a carbonyl group. Okay, so this is a real example of this molecule. So this is a ketone, and you can see we have this carbonyl stress here. And carbonyl, the exact wave number might differ somewhat in different types of molecule, either in ketone, aldehyde, or carboxylic acid. So in a simple ketone, it's around 7 to 10. But when it's in carboxylic acid, how do we know it is a carboxylic acid? And of course, we need to see this carbonyl stretch around 7 to 10. And also because the acid has the OH bond as well, so we should see an OH stretch as well. And as you remember from the last slide, the OH bond should be a very broad and very large peak around 3,000. So around 3,300. So basically around here. And combining this and this one, we can very comfortably say that we should have a carboxylic acid group in this molecule. Okay? And because of the effect of the carbonyl, you can see the carbonyl bond is very close to the OH bond here, and it can affect the bond strength of that. So actually, it will lower the bond wave number a little bit. So remember, for an alcohol or regular OH group, it is around 3,300. But in the carboxylic acid, the OH will absorb at a slightly different one. And actually, usually it's a little bit smaller than 3,300. For example, this one, it's around 3,000. Okay, so a little bit smaller. So basically, if you see these two appearing at the same time, it's very likely a carboxylic acid functional group. Okay, and the last one, the aldehyde, basically this group. So we have carbonyl and we have a CH here. So the feature of that one is the CH signal, which is a single bond CH stretching, right? So we know it should be below 3,000. And if it's in an aldehyde, it should have two close peak at around 2,700 and 2,800. So let's see an example. So this is a aldehyde molecule, and below 3,000, that should be the CH stretching. And we see two group here, 2,820 and 2,720. And we also see a carbonyl, very strong absorption and sharp peak here. So we know it has aldehyde group, and because we see these two close CH stretching, we know it's probably aldehyde. All right? So that's how we can really narrow down the type of functional groups we have from these featured peaks. Okay? The carbonyl stretching group of the amide, so when it is connected, the carbonyl is connected to a nitrogen, it absorbs at even lower frequency. So the frequency is no longer at 1710. It will be lower down to about 1640 to 1680. So example here, we have the carbonyl connected to this NH2 group. So we can see the shape is still quite strong and sharp, but we can see that it's quite shifted to a lower end. And of course, we need to able to see this the nitrogen stretch, the NH stretching as well, and it should match what we have learned for the age stretching. For example, if this is the primary amine, we should be able to see the double peak at 3300, and we do see that for this molecule. So we can deduce that this carbonyl is connected to a primary amine, which is like this. All right, so that's the main functional groups we will be looking at. That's also the most characteristic one. So for your assignments and exams, you only need to concern about those most featured functional groups. So to summarize, if, for example, in your experiment you did IR spectroscopy analysis, and for your compound, this is the spectrum that you get. So how should you read it? So first, you draw a line at the 1500. So we discard anything on the right. So that's the fingerprint region, right? It's too complicated, and we couldn't really tell had much more information from here. Of course, you can feed it to a computer, and the computer can probably give you a match on the fingerprint region. But to start with, we just don't look at it. Okay? And then we only look at the one on the left of the 1500 with number region on the left of it. So first we'll look at the broad feature. We'll see always there a broad peak around 33 or around 3000 with number. If we see that, we can know that there should be a OH stretching. Remember that because of the broad feature of the OH peak, sometimes many other features will be buried into this broad. So you have to really look at carefully on the side of this big peak. Do we have any other featured peak, because it may overlap with this OH stretching. Okay, so once we determine that, next thing probably we need to draw a 3000 line, and we will see below and above it to look for the CH stretching. Remember, for the single bond and double bond, single bond is right below the 3000 on the right, double bond is right above. So if we see that peak, we can assign it to the CH stretching. And even further on the left, if we see it at about 3300 or higher, we can have in mind that probably we have a triple bond CH stretching. And of course, we need to look at the 1700 region to look for those very sharp carbonyl peaks as well. Okay, so that's the most characteristic peak we should looking for, from the beginning. And this spectrum that I'm showing you an example here is actually a spectrum for aspirin. And aspirin has a molecular structure like this, and I'm indicating those functional groups with different colors, and you can look back after class to see whether they match what we have learned in earlier, and you can try to imagine how you interpret this structure. If you don't know it is aspirin, right? You can try to see whether I can myself can tell they have those types of functional groups just simply from those spectrum. Okay, so it can be an exercise. To help you organize your thoughts, here is a summarizing spectrum of all the functional groups that are most characteristic. So you can try to organize in your mind what I've learned before, and this figure can help you memorize those rules. So it will help you to memorize them if you understand it, like what's the relationship between atom weight versus the frequency, what's the relationship between the bond strength versus frequency. So that will really help you to order them it's not quantitative. It cannot tell you how many functional groups are there in a molecule. Like if there are 5 OH group versus 1 OH group, it will look, you cannot really tell, right? So you just see a big peak at the OH wave number, but you don't know how many there are, all right? It only can tell you whether there is or there isn't based on the presence or the absence of the feature peak, okay? And the fingerprint region, which is the one that we haven't really talked about, if 2 pure compounds show identical fingerprint region pattern, they are the same compound, all right? So in this way, we can characterize the purity of our product. And the other way also works. If they are the same compound, they should have exactly the identical fingerprint as well. If you see even a tiny difference in the fingerprint region, they are different molecules, all right? And also, the IR cannot provide detailed structure information. So all it can do, the best it can do is to tell you the function groups, but it cannot tell you what's the arrangement, how the function groups are connected, or what's the position, what's the location of the groups in the backbone. So that's you cannot get from the IR spectroscopy. So to get more information, IRs is usually in combination with other analytical tools like mass spec or NMR to really give you the accurate structure. But it's a good start. And sometimes it's like a quick and easy way to differentiate different molecules. All right. And this table is a more quantitative, accurate summary of different function groups, and you can look at it and try to find your own way to help you to memorize them. Okay, so next I want to give you some exercises, and so these exercises can help you to really understand, to see whether you can grasp the concept. So I know you probably have the next slides on your laptop, but just try to ignore them and think for yourself. So we have a spectrum in our hand like this, and we have 5 candidate molecules. We know it's one of it, but we don't know which one is it. So your task is to determine which molecule this spectrum belongs to based on their feature. All right? And we have a few more others to look at. So now I want you to take like 5 minutes for yourself and really just follow the logic that I have showed you in here, and try to determine which one this one belongs to. All right? So I'll give you like 5 minutes to think for yourself, and then we'll once you look at this spectrum, first thing you notice is this very broad peak at 3000. All right. So this one it corresponds to an OH stretching. So we can eliminate any molecules that doesn't have a OH. So basically, this one and this one doesn't involve a OH group, so it cannot be either, these two. And let's look at some other features. And we see like at 1700, we see this like this is the strongest peak in the spectrum, and we know that it probably corresponds to carbonyl. So it should have a carbonyl here, and so we select only the one that has carbonyl. So actually, this is the only one that should be left, just based on this summons of these two groups. And you can you can check whether it matches other functional groups, like the double bond. Like the double bond should be like above 3000, but it probably will be buried under here, so we don't really observe it. So just based on the two function groups, we can actually screen out it's this one. Okay. And similarly, if we're given this one, so maybe you can take like 2 minutes to quickly select it. It's also one of the molecules that's in the above. So so that should be quite intuitive. Again, for the strongest peak at 1710, we saw this one, so that should be a carbonyl group, and only this two contains carbonyl. So to differentiate these two, the quickest way probably is to see whether we have a OH stretch or not, because this one has OH stretch, but this spectrum doesn't, because we don't see a broad peak around here. So it has to be this one. And if we double check it, this one, if we draw a 3000 line here, we notice all the peak lies below this, the 3000 line. So that means we shouldn't have a carbon-carbon double bond on CH stretch. And indeed, this one doesn't have, so which is consistent with what we saw here. Okay, so that is how, okay, so yeah, this is another examples that I already labeled all the possible peaks. You can take it as an exercise in the after this class to check whether it matches. And some exercise here, so it asks you to determine the function groups and which one it corresponds to. So you should be able to write down the information yourself. So I'll just leave it as a after class exercise for your own. So there's answers on each one of them, so you can. But I encourage you to think about it yourself first too, and then check the answers. All right. Any questions before we move on to the mass bank? Okay, cool. So as I just said, the IR has many limitations. So it has a limitation that it can only inform the presence and absence of function groups. So it's quite a crude information. It does not tell us the size of the molecule, because no matter what size is it, as long as it contains the corresponding function groups, we will be able to see it in the spectrum. So it has nothing to do with the size of the molecule. And also does not infer what heteroatoms are present. So the heteroatoms are the atoms that not carbon, oxygen, nitrogen, or hydrogen. So some other they are present. Okay, so these are just three of the like limitations, like very significant limitations are. So, but on the contrary, mass spectrometry actually can provide those complementary informations. So they are quite good complementary tools to use. So IR spectroscopy, as we said, it involves absorption or emission of light. So for mass spec, so the full name is mass spectrometry. So it's just a little bit different in the term, but spectrometry actually does not involve light, so it's not interacting with light, but interacting with something else. So, but it still has a spectral in front of it, so you can know that it still generates a spectrum as a function of something, and just that something is not wavelengths anymore. Okay? So what mass spec can tell us? It can tell us the molecular weight from a very small sample. So we don't need to provide like grams or maybe even milligrams, or sometimes very tiny amount of sample is enough. And it does not involve the absorption or emission of light, as we just said. And it's a beam of high energy electrons breaks the molecular apart. So the idea of the mass spectrometry is that you don't know what the molecule structure is. It's like a black box, but you break it with high energy electrons, just like you drop a toy or whatever you want to study on the ground. It will be broken into pieces, and that pieces you can analyze with this instrument. And from that pieces, you can get a lot of structure information. So that's the idea of that. And the way we break the molecule is through high energy electrons. And the masses of the fragments and the relative abundance reveal information about the structure of the molecule. So let's first look at the instrument, how the instrument is built. So as we said, we need to break up those the molecules that the samples we want to analyze. So actually, first of all, the tiny samples are injected into these vacuum tubes. So they are first ionized in the high vacuum. So they are vaporized into gases. No matter what format, the sample you provide can be solid or liquid, but once they go into this high vacuum tube, they're all vaporized by heating. So after vaporized, it will be bombarded by electron beam. So these are very high energy electron beams. So their energy is so high that it can break the bond in your molecules. And so in this way, your samples are actually broken into pieces. They are no longer the original complete form as they were before. And then they are accelerated. Some of them will be charged by breaking to pieces, and they will be accelerated. So they will acquire some speed, so they can travel into this tube. And when they travel to here, there is a magnet creating the magnetic field, because like from physics, the charged molecule, when they going through a magnetic field, they can like feel the Lorentzian forces, which can bend in their path. So based on their charge and their weight, they will be bent into different extended. So basically, based on how bent their path is, they will hit at a different location on the detector. Okay, so basically you can infer from the location on the detector their charge and mass ratio. Okay, so here is probably a more realistic illustration of the mass pack. And usually the mass pack is, as I said, they need to be vaporized before analyzed. So they are usually connected field and then detected by the detector. And based on the location of the detector, they will be, you can infer their charge as well as their mass. So you can calculate ratio, and based on that, there's a lot of information you can get. So so you can usually see a GC mass MS combination in the instrument, and that is commonly used for drug identity determination. Okay, so that is on the equipment side. So here is how it works on the molecular level. How do we ionize the molecule? So, for example, the simplest example we can have is a methane molecule, like CH4. So when we have these high energy electrons, so like this electron beam, when it hits this methane molecule, it will break some of the bonds, and this molecule can break apart in many different ways. One way is it may lose an electron, so that would be like the simplest way it can break up. And it loses an electron, and so the rest of it remains intact. So and if the molecular weight is m, this part would be m plus, and we will call it a radical cation because it contains a positive charge. So that's what the cation means. So you can now you can see it is a charged molecule, so that it will be affected by the magnetic field in the mass spectrometer. But however, when the molecules become more complicated, like for example ethane, it's one more carbon compared to methane, it can break up into many other ways besides losing an electron. So if it loses an electron, it will has this molecular, it will has this form, and we actually has a name for this type of breakage. We call it molecular ion because that's the largest pieces we can get, just losing one electron from the original one. So we call it, we denote it as the M plus, and we call it molecular ion. Okay. But some other way it can also break up. For example, it can also lose a hydrogen atom here. So you can see in this way, the piece that we detect will have a slightly smaller M to Z mass to charge ratio. So the molecular ion is 30, but this piece will be 29. So you can imagine they will hit at the different location on the detector. And furthermore, it can also break up at this bond, so it will generate a 15 M to Z ratio segments, which will be collected at a different location as well. Okay, so you can imagine when the molecule become even more complicated, there are many other ways it can can be broken into pieces as well. So we will collect, depending on the M to Z ratio, it will hit different position on the detector, and we will tune the magnet strength so that only a certain M to Z ratio can really be detected at the detector. And then in the next week, we will change the magnet strength again, and another different M to Z ratio will be detected, and then again and again. So that's how we can build up this spectrum. And on the x-axis is basically the M to Z ratio, and on the y-axis is the bandwidth of the segments. So the more easy it be broken into a certain way, we will see a higher abundance for that for that segment, basically for that M to Z ratio. All right, does it make sense? Okay, so you can see the shape of this spectrum, or the profile of those peaks can really give us how, like which one is the easiest one to break, what's the most stable segments, and that actually tells us a lot about mass spec will look like. So, and there are some terms that we need to learn, some feature of the spectrum that we can get information from. So, okay, first, you notice it's all normalized to the highest peak. So no matter so mass spec is not a quantitative tool, so it cannot tell you how much sample you have because it's all normalized. It's all normalized by the highest peak. So the highest peak, we call it the base peak. Basically, that's the strongest peak and defined to be 100%. So all the other peak are a relative value compared to this base peak. And another feature, another thing we should look at is the molecular ion peak, the M+. So that is the peak that is the highest after the ratio on the spectrum. You notice it's on the most right part of the spectrum. And also, sometimes people call it the parent peak because that is the molecular ion peak is actually your original molecule just losing 1 electrons, right? Just like we said before. So this actually will tell you the total molecular mass of your molecule. All right. So if you see it's 100, you know, oh, my molecule has molecular weight of 100. And you notice many cases the base peak is not the molecular ion peak. So basically, this peak would be the most easiest bond to break. Basically, your segments is the most stable one among all other segments. So that creates the base peak. So basically, that's the weakest bond in the molecule. Okay, so that's two very important concepts, and you need to understand what they mean respectively. Okay, so here's the real spectrum of an example molecule. So this is a molecule. It's an ethyl benzene. So it's a benzene ring connected to a ethyl group. So it has a molecular weight of 106. What it will look like if we get the mass spectrum of it. So you see we have a molecular ion peak at 107, which corresponds to the parent peak, which is here. And we have the base peak with the most stable one at 91 because this bond is the weakest bond, so it's tend to break most easily when it's hit by the electron beam. So you get a lot of this benzene. Not this bond, like this bond here. Between these two carbon. So this is very easy to break. So you have this one left over. So you see base peak at 91. All right. So that is how this one would look like. So now you'll see. Okay. So we now understand what they mean, but how exactly can it tell us the structure information? Okay. So, one thing you need to understand that nowadays the mass spec instruments are very accurate. So we have reached a point where we can really detect, measure the weight very accurately, down to like 7 or even 8 digits after the digital point. So that's actually very helpful. So that instrument is called a high-resolution mass spectrometer. So it is has much higher resolution than the traditional mass spectrometer, and it can measure masses up to 1 part in 20,000. So it can give us like very tiny differences between the molecules. So one thing you need to understand is that probably in your middle school you learned that the atoms has masses around the integer. You see like carbon has a mass about 12, hydrogen has 1, oxygen has 16, nitrogen has 14, something like that, right? But in reality, they are not exactly integers, so they are like this. So I'm listing the real accurate molecular weight they are around 44, but not exactly 44. This table gives you the more accurate molecular mass of each of them. So you can see, using this high-res mass spec, we can actually measure the molecular mass down to many digits. So, for example, we measure it at 44.029. Then, based on this table, can you pick out which one it should be? Right, so you should pick the one that is closest to this number, which is this one. So, because we have high resolution, these are actually quite different. Alright? And this one is the closest one to the exact mass we measured. And so we know it has to be this molecule instead of the others. Okay? So this is just one advantage of how we can, why the high-res mass spec can really help us determine the exact molecular structure, like molecular equation, I would say, at this point, of your samples. And also, it's naturally in the environment, for example, this is the molecular equation that we write for our molecules. But you know, like each atom has isotopes, and each isotopes they differ slightly among them. And luckily, in our environment, the isotopes are naturally occurring. So, for example, the carbon, they have most of them are carbon 12, but some small portion of it is carbon 13 or carbon 14. So that will slightly change the overall molecular weight, and our high-res mass spec can actually detect that differences, which can also really help us to determine the molecular equation of our molecules. So I will stop here today, and we'll continue for the next week lecture on this part, and we'll finish the mass spec and start the NMR for the next lectures. Okay, so let's have a few minutes break. We'll come back at 2 and to discuss the assignments, number 3 assignments, and I will upload the answers now. Okay.
We're going to do that now. What in-class exercise? Oh, I tried. No, cause like this. No, it's possible. Like, it's definitely possible. But then, like, I only just understood how the up-amp, like the 1, 2, 3, 4 that thing the other day. So when I look at the circuit, because you're supposed to, the second question is that you're supposed to fix the circuit, fix out, like connect some other stuff. So like I'm still confused about it, so I cannot grasp the concept yet. I asked for the answer, but she said she hasn't done it. I said, oh, send to me when you're done. And she's like, I don't know if I'm even gonna do it. There's actually no point. I think it's like more like, I think it's effort based. That's what I think. Because even for, let me show you. exercise 1. Oh, it doesn't say here, but on like the laptop it says does not contribute to your grade. Yeah. So I'm gonna try. If I can't do it, then I'll let it be. I think you should focus elsewhere. I'll do the lab later. Yeah, it's kind of the same thing again. I looked through it already. Like 4 different stuff, but I think the same platform, like the blast. Oh, I think I found the spot. I think I found the spot on my neck. Just keep pressing. Left. Yeah.
I tried massaging mine. I tried to. I asked my friend to massage it. It hurt a lot when he massaged it.
In a good way or no?
Like he really pressed on the.
So is that a bad thing?
I don't know. It